We already know that we can represent any rigid motion as a screw motion. And we can represent this screw motion using exponential notation, where S is a matrix with the parameters omega and V. And V, or omega, is a unit vector pointing in the direction of the screw motion, represented in skew symmetric matrix form. And V is found using the relation where Q is any arbitrary point on the axis of rotation, and H is the pitch of the screw motion. We've also seen that we can represent separate rigid motions as successive screw motions by multiplying their exponential forms together. The product of exponential formula takes advantage of this by representing the position of the end effector as traveling in a screw motion about the axis of rotation of each joint. So let's imagine for a second that we have a generalized open end-link chain for which we've already defined the following things. First, we have a fixed reference frame, and this can be arbitrarily chosen. Also, we know the zero displacements of each joint. We also have attached an end effector to the final link of the chain, the final link of the chain. And this can be also, it can be arbitrarily attached to the final link. And the reason that we can have an arbitrary fixed reference frame and an arbitrarily attached end effector is that the first thing that we're going to do is define the transformation which describes the end effector in the reference frame. And so for this, we'll use M, which defines the homogeneous transformation of the end effector in our fixed reference frame. So if we want to describe the state of the end effector in the case where we have zero displacements of any of the joints, we can imagine what this will look like. But let's say that we allow just one of our joints to move. And we can imagine that this is a revolute joint. So the end effector is now traveling in a screw motion about the center of rotation of this joint. And because it's a revolute joint, the pitch of the joint is 0. So it's just traveling, the end effector is traveling in a circle about the center of rotation of the joint. So in the case where only one of the joints is moving, we can describe the state of the end effector using this notation. And if we want to add a second joint, we can multiply the exponential notations of the screw motions, which describe the motion of the end effector about each of these joints. So it's easy to see what the final generalized form of the product of exponentials formula will look like. But let's first think about why it's useful for us to use the product of exponentials formula when we're deriving forward kinematics. So first of all, the product of exponentials formula is very useful because we don't have to define fixed reference frames at each of the joints. Instead, we just need to know the axis of rotation of each joint. Additionally, the derivation of forward kinematics with the product of exponentials formula becomes simplified with certain types of joints. Like we just saw, if we have a revolute joint, then the pitch is 0. And so V is just defined as the cross product between omega and Q. And also, if we have a prismatic joint, which just travels in one dimension, we can imagine that omega is 0, all terms in the omega skew symmetric matrix are 0, and then V is simply a vector that points in the direction of the displacement of the prismatic joint. Finally, as we saw, we can define the fixed reference frame arbitrarily, and we can also attach the end effector arbitrarily, which can simplify calculating, or can simplify finding the forward kinematics of an open chain for us. So the last thing I'm going to do is write the generalized form of the product of exponentials formula, and we'll look at how we can go about finding the parameters of each of these terms in following videos. I'm going to move this back. Thanks for watching.